Welcome back to the first law of thermodynamics in physical chemistry. My name is Kevin Tokoph. Make sure to like the video and subscribe to the channel for future videos and notifications. Alright, so in this video we're going to talk about something referred to as a quasi-static reversible process. And most of the time that you talk about these processes, you just call them reversible. Now, what is a reversible process? A reversible process is one process in thermodynamics that maximizes the total work possible in a given system in a given process. Okay, so most of the processes we're going to be doing in the initial part of thermodynamics is we're going to be expanding or compressing a gas. We can be heating the gas and so forth. So we can be changing pressure, volume, and temperature, basically. Okay, and for this video, we're going to use the ideal gas equation of state, that the pressure is equal to nRT over V. Okay, that's the ideal gas equation of state solved for pressure. That's what we're going to be using. Now, if you notice that essentially one way we can write this is pressure is equal to nRT times 1 over V. If we're looking at pressure in relation to volume, it's going to be sort of this curve that looks like this. It's going to approach infinity at V equals 0, and then P is going to approach 0 as V goes to infinity. All right. So this graph is actually what's referred to as an isotherm. And what it's essentially referring to is this temperature, whatever temperature is specified there, that's actually this temperature right here on this curve. Anywhere on this curve is the same temperature, it's just that the pressure and volume will vary. So it's an isotherm. Okay? And what we essentially want to do is we want to figure out which process maximizes work. Let's suppose in this we are going to keep the temperature constant. And all we're going to do is we're going to change the volume of a particular container. So we're going to change it from V1 to V2. Now, notice what I'm representing by these rectangles. So in other words, you could consider this rectangle 1, rectangle 2. What I'm essentially doing is I'm saying if I move from V1 to some point in the middle, we'll just call it VA, and then I move from VA to V2, then I'm doing this essentially in a two-step process. Okay, now notice, if I'm doing this from V1 to VA, I look where that essentially hits the curve, and it hits it right there. So this right here is going to be representative of pressure 1. Okay, that's the height right here of this rectangle. If I'm looking at where VA to V2 hits the curve right here, that's essentially pressure 2. Remember that the definition of work, the classical definition, is that work is equal to F delta X. So remember, you can actually rearrange this a little bit, do a little manipulation, and get PV work, and you get that the work, in the case of physical chemistry, is negative P delta V. So that means what I need to do, P delta V, this distance right here essentially, this is a delta V right there. So if I want to find P delta V, which is this, times P, which is in this case is P1, that's just the area of that rectangle. Area of a rectangle is the base times the height. The base is delta V, the height is just P1. If I want to find the area of rectangle 2, it's again base times height. The base is still delta V because I've broken it up such that these intervals are the same, and the height is just going to be P2. All right? So if I wanted to find the expression for the work, I'm going to multiply the total pressure times delta V, but that's going to be negative, and I put this in parentheses, P1 times delta V plus P2 times delta V, and I can actually pull the delta V out, and I can get that this is negative delta V times P1 plus P2. And that's my expression for the PV work done if I do this in a two-step process. Now, notice that you can clearly see there are regions here, and I'll kind of show you which ones these are. Let me do it in yellow so it's easy to see. There are regions here, i.e. these regions right there, that you can clearly see are under the curve. In other words, it's bound between V1 and V2. It's under the curve, but notice that those rectangles don't occupy that area, right? Anytime you have a process where when you do it in a two-step process per se, and you have areas like this that I've shaded in yellow that are not occupied by the rectangles, that's what you technically term an irreversible process. In some way, the process is irreversible. In some processes, you could consider more irreversible than others, as we'll see in the next one. Okay, but essentially, it's not reversible. Now, what does reversible mean? It means you maximize the work. Well, notice because we're only taking into account the area of these rectangles and we discounted the yellow space, we have not maximized the work because the work is technically all the area under this curve. Okay? So because we have not maximized the work, in other words, we don't count this yellow part, well, then that just essentially means that it's irreversible. Okay? Let's look at the next example. Okay? In this case, we're going from V1 to V2 as well, but notice in this case, I have 5 rectangles, and I'm still going to call these intervals right here. This is delta V, that's delta V, delta V, delta V, delta V, such that each of those delta V's is 1/5 of the total distance between V1 and V2. All right, so I'm going to do kind of the same thing. I'm going to look to see where this rectangle right here intersects the curve, and I can see it intersects, I'm going to just call that P1 again. The second one intersects at P2, P3, P4, P5. So I'm just going to kind of do the same thing. I'm going to find the total area of all the rectangles there. All right, so the work is, PV work is going to be negative P delta V, but all the pressures times their delta V's is going to be P1 times delta V, plus P2 times delta V, plus P3 times delta V, plus P4 times delta V, plus P5 times delta V. And notice what I can do again, and I can group these any way I want, but I can group all the I can pull all the pressures out because they're all multiplied by delta V, and I can get that the PV work is equal to negative delta V times the quantity P1 plus P2 plus P3 plus P4 plus P5. Now, notice in this case, there are still components here, all right? There's still components there that were not counted by using this rectangle method, all right? There are still components that are not counted, because these yellow areas, again, they're still under the curve bounded by V1 and V2. They're still under the curve, but they weren't counted when we calculated the work, when we did this rectangle method. So this is also an irreversible process because we didn't count this area under the curve, because the work is the area under the curve. We did not maximize the work. Now, my question to you is, between this first situation and the second, in which case was more work done? Well, there was more work done in the second case, okay, because there is less of this yellow space. In other words, the rectangles that I used, I strategically was able to use more of them, and so as a result, they're thinner, and so I'm able to occupy more area under the curve by the rectangles. So this over here, this is actually a 2-step process. That's the first one I did. This is a 5-step process. So hopefully what you can see here is that as long as I'm going between the same volumes, and I am here, it's the exact same process, but in the first case I only used 2 steps to do it, 2-step irreversible. In the second case, I did a 5-step irreversible process, and you can hopefully see that as I increase the number of steps, I increase the work done. Okay, so that means that the more rectangles I have in here, the closer I get to maximizing the work. Okay, so how do I get, what's the maximum amount of rectangles that I can get between V1 and V2? Well, since V1 and V2 are finite numbers, you might be tempted to say it is a finite number, but I can actually theoretically get an infinite number of rectangles between V1 and V2. And you might be able to see where this is going. Now, because the distance between V1 and V2 is finite, how can I get an infinite number of rectangles between there? Well, if you have an infinitesimal distance in terms of volume, in other words, dV as a distance, then you can get an infinite number of dVs between V1 and V2. And that's what we're going to show over here on, let me move this down here. That's what we're going to show over here on the right. In this case, I obviously haven't indicated all the dVs because they're infinitesimally thin, right? And there's an infinite number of them. But I just sort of maybe blown one up so you can, hopefully visualize it. That this one right here, this is dV. Okay, they're all dVs, and there's an infinite number of them between. There's an infinite number of them between V1 and V2. All right. So again, what you're doing is you're just going to sum all the little rectangles. Well, what's a rectangle? Well, the base is dV, and what's the height? Well, the height is just the pressure wherever I am on this curve. But here's the problem with just simply writing it as the sum from 1 to infinity, because there's an infinite number of these dV's, the sum from 1 to infinity of all the p's times dV. What's the problem with that? Well, there's an infinite number of them. So how could you possibly, in a finite amount of time, in your life, how could you possibly add up, all of an infinite number of these dV's times the pressure where you are on the curve? You can't do that because there's an infinite number of them, okay? And depending on where you are on the curve, this pressure right there is going to be a different pressure right there than it's going to be a different pressure right there, because they all are actually at different volumes, because the pressure varies with volume. In other words, the pressure is a function of volume. Okay, the pressure varies with volume. Well, how does it vary with volume? Well, it's the ideal gas equation state, nRT over V. Okay? So, in other words, what I'm going to do is, in place of this summation notation, I'm going to replace it with an integral. Okay, so wherever I see the sum from 1 to infinity of all the pressures as a function of volume, I'm going to write that as the integral from V1 to V2, because I'm expanding from V1 to V2, of P as a function of V dV. Now, because P actually varies with volume, and I want to write it in terms of volume, I'm going to take this, I'm going to do this in a different color, I'm going to take this P as a function of V and substitute it for nRT over V and just keep the dV there. And now what I have is I have an integral. So the PV work done with an infinite number of rectangles here with base dV is equal to negative nRT times the integral from V1 to V2 of dV over V. And hopefully by now you know what this integral is. If I evaluate 1 over V dV, that's just going to be the natural log of V2 over V1. And then I'm multiplying that times negative nRT. And this expression right here is going to be the work done through a reversible process. Now remember, what did we say a reversible process was? A reversible process was one that maximized the work. Well, when we didn't maximize the work, remember, we had these spaces up here that still had that yellow in it, and that was representative of still area under the curve, but it wasn't counted because the rectangles were too wide, and they leave some space. Okay? However, think about this, just think about this. If I have rectangles that are infinitesimally thin, meaning they're so thin that you can't even see them basically, well, is there going to be any yellow space? And the answer is no. There's going to be no yellow space. All right? No yellow space there, which means that all the area, all of the area is going to be accounted for under this curve. And because work is the area under the curve for a PV graph, okay, then the work is maximized. So this right here, this is the reversible process. So this concept of reversibility has two implications, okay? Number one, just about any time you're doing a reversible process, there are exceptions to this, but you need to think about writing it as an integral. Why? Because you can have graphs that look very different than this, but if you want to maximize the area under the curve, you have to do these little rectangles, right? And so that implies an integral. So a lot of times whenever you have a reversible process, you need to think about writing it as an integral, okay? What's the other implication of this? Well, here I have two rectangles, and that implies a two-step process. It's irreversible. Here I have 5 rectangles. That implies a 5-step process, also irreversible. Now the one we just did was reversible, but how many rectangles do I have? What is my number of rectangles with width dV in this one? It's infinity. So if this was 2 rectangles, 2 steps, this is 5 rectangles, 5 steps, how many steps is the reversible process in theory? It's an infinite number of steps. And if you tried to do an expansion of a gas from V1 to V2 in an infinite number of steps, you can't do it. You'll be dead, and quite frankly, the entire human race will be dead by the time. In fact, it'll never get done, basically. Okay. So the point is that a reversible process technically is not possible. It's actually not achievable. Now, there are things you can do to get pretty close, but the point is a reversible process is imaginary. Okay? You're imagining doing this in infinitesimally small steps, okay, to maximize the work done by an expansion or a compression. Or you can also do it for a heating, and we'll look at that in another video. So the key is that under normal conditions, reversible processes, true reversible processes, are not achievable, okay? But what they do show you is the maximum work done. So let me ask you a conceptual question based on what we talked about. So if I were to do the same thing, expand from V1 to V2, and let's say I had two graphs here. Let's suppose one of them had 15 rectangles, another had 30 rectangles. In which one did I do more work? Well, if I do it in 15 steps, there's going to be a little bit of yellow space here under the curve. But if I do it in 30 steps, there's going to be much less of that yellow space. In other words, in 30 steps, I'm going to do more work than in 15 steps, okay? Now here's another question. If I were to do this in one step, that would be completely irreversible as it can be. And you'd only have one rectangle here, and that would have the least work done. So the least work you can do in an expansion or compression is when you do it in one step. The most work you can do, in theory, would be if you did it in an infinite number of steps, and that's a reversible process, okay? And because there's one other thing that's really important about reversibility in thermodynamics, okay? The other name for it that we often use, and you often see this less, but it's quasi-static. Why is that? Well, we have this concept called internal equilibrium. Okay, now here's this, imagine this ideal gas equation of state. P is equal to nRT over V. Again, I'm keeping temperature constant, okay, but what I'm going to do is I'm going to change the volume of the container, and then I'm going to see how pressure changes. Now, hopefully we know Boyle's law by now, that if I increase the volume, you can see that the pressure drops a little bit. All right, so if I think about doing a reversible process, here's what I'm doing. I'm going to increase the volume initially from V1 an infinitesimal amount dV. Well, then that's going to change the pressure by an infinitesimal amount dP in proportional to nRT. Okay? So, in other words, if I change the volume by dV, I'm going to change the pressure by dP. Okay? So, in theory, what quasi-static means is I'm going to slowly, very slowly increase the volume dV. That's going to change the volume by dP. And then I'm just going to wait for everything to resume equilibrium. So the key with quasi-static reversible processes is they have to, after each infinitesimally small step, the system has to resume equilibrium. Okay? So if I were to just do this in one step or two steps or 5 steps, okay, I'm not allowing for the system to regain equilibrium. I'm just going for automatically from V1 to VA and then VA to V2. Okay, the system isn't reestablishing equilibrium. It has to be homogeneous in terms of the gas distribution, essentially. Okay, the temperature has to be constant. Okay, so if I go from V1 to V2 all of a sudden, and I'm changing it that fast, the pressure is just going to change really quickly, and you're not going to be in internal equilibrium. Okay? So, in other words, by changing it only an infinitesimal amount dV, and the pressure goes down dP, then you kind of sit, you let it retain equilibrium, and then you crank it up again dV. And then the pressure is going to fall another dP. And then you establish equilibrium again, then you crank up the dV again, another dV. Pressure falls by another dP, and you just keep doing that over and over and over again. Okay? There's one other analogy that you can sort of think about with this. Okay? Imagine if I have some kind of container, like here's a movable piston on top, a container with gas, right? And this is the top of the container. And imagine on the top, I have a bunch of grains of sand, right? And we know that if we put weight, mass on top of a container with some weight, mg, that it's going to apply a force down and compress the gas that's inside here. So it's going to compress all the gas in there. Well, if this is a bunch of grains of sand, the closest thing you can really get to a truly reversible process is imagine you have a bunch of the sand on here. And then what I'm going to do is I'm going to take off one grain of sand at a time. Well, that's going to decrease the weight on top, and this is going to expand a little bit. In other words, increase the volume dV. Then the pressure is going to drop by dP. And then once it regains equilibrium, I'm going to take off another grain of sand. That's going to increase the volume a little bit dV, and then that's going to drop the pressure dP. So in theory, what you would have to do in this system or this situation is you'd have to take off one grain of sand at a time, one at a time, until all the grains of sand were gone. And that would get you closest to a reversible process. In theory, it's still not, but it would get you the closest. If you were to just have just one, instead maybe if that's not sand, if this were just like a rock, just one solid rock, and you just took the whole rock off all of a sudden, that would be like doing this in one step, and you'd have a graph that would, it would actually be less work than this graph right here, because you'd be doing it only with one rectangle, okay? That's an irreversible process. You're taking all the weight off at once, and so the work would be minimized if you had a rock and you just took the rock off all of a sudden, because the gas would just go from V1 to V2, and then it would drop from pressure 1 to pressure 2. Okay? So hopefully this gives you a little bit of intuition on what a reversible process is and what a quasi-static process is. They're basically the same thing, and hopefully you understand the implications of it. If you get anything out of this, remember that a reversible process maximizes the work done by a system by a given thermodynamic process. And the other thing is that the more steps that you have, in other words, the more rectangles you have, the more work you're able to do. And the most rectangles you can have is infinity, and that's an integral. See you in the next video.